In this lesson, we're going to build off of last lesson where we learned how to derive a function that of the form a times x to the n power. And since we have that new rule, we sort of want to explore its limits and where it breaks down and that sort of thing. So in this lesson, we want to show that if we have functions that don't really look like that, like so here's a function that's not a times x to the n, but what we can do is we can take this function and break it up into smaller pieces. We are allowed to do this, so as long as these terms are separated by an addition or a subtraction, we can split them into smaller pieces and then take the derivative of each of these. And so each of these little pieces all follow our rules that we studied in the last lesson, and so we end up getting this and we add it all together, and so our final answer, the derivative of this function, is this function. Again, over here, we don't have a rule that where we can take the derivative of this product here. But if we do a little bit of manipulation, we can distribute here and we can get two terms now that are separated by plus or minus, and each of these terms individually follow the rule that we learned last lesson. So we can apply our derivative rule to each piece, find the derivative of each piece, and then put them together at the end. And so this ends up being the derivative function of this. And so the lesson is that we can take a function that's given to us, do some algebra in advance, twist it and turn it in a little bit, and then be able to apply our new rule. So that's the first part of our lesson. The second part of our lesson explores this question about the second derivative. So we have an original function and we create the derivative function. Now that's a function. Can we take the derivative of that then? And the answer is yes. And so I've written sort of an original function in the two sort of notations that we have to get good at. And so here's the original function. If we take the derivative, it looks like this. This again is a function, so we take the derivative of that and we get this new function. And so we have this f double prime for denoting the second derivative. And over here, they write it a little kind of a little different. Instead of the 2 being with the y, it's over here with the d, and that's just to show you that that this is the second derivative as opposed to the derivative of a y squared function or something like that. So this is the actual correct notation like this for the second derivative. So can we take the derivative again? Yes, we can. Yes, we can. So what we do is follow the rule again. This should be replaced by a 12. That would be the third derivative. We'd write it like this. And then we could actually take the derivative of 12 and find 0. And that would be the fourth derivative. Can we find the fifth derivative? Yes, we can. What would it be? It would just be 0. And the sixth derivative would be 0. And it would just keep on going and being 0 from here on out. So here's the second, third, fourth derivative. Now that we can find it mathematically, what would the second derivative mean? Since the derivative is a function that tells us the rate of change, the rate at which the function is changing, then the second derivative tells us how much, or the rate at which change is changing, which is hard to get your head wrapped around, but that's essentially what we're doing, and it has applications in physics. For example, acceleration, and we'll see some other examples, real-life applications of the second derivative in class. But that's it for this lesson.